Hello, this is my fourth lab report for Physics 2211, in which the motion and mass of an object swinging in an arc and oscillating on a spring is observed. The purpose of this experiment is to observe the motion and mass of an object swinging in an arc and oscillating on a spring and create a model illustrating the energy changes in motion. This is accomplished using Newton's second law and the energy principle. Using these two formulas will allow us to see the energy principle in practice, since delta E will be zero if this experiment truly upholds the principle. I used Tracker to create an observational model and collect the motion data, and used GlowScript to create a computational model based on the initial Tracker conditions. The results of this lab showed the energy principle was upheld since delta E equals zero. However, the computer model did not exactly match up with the observed data, making it a poor fit for the mass's oscillation on the spring. There are several fundamental principles behind this lab, including Hooke's law, the energy principle, and Newton's second law. The motion and velocity of the mass on the spring are calculated using Newton's second law, and Hooke's law calculated the force of the spring on the mass. The energy principle keeps track of the work done in the system, which was important in determining if the energy principle was upheld. I chose my system to be the mass, spring, and the Earth. Here is the video that was uploaded to Tracker. As you can see, the X and Y values oscillate nicely in the shown graph. I edited the frame rate to match the edX video and used frames 6 to 105 to shave off unnecessary frames. To set up the experiment, I found the mass from the edX videos as well as the frame rate in proper frames. The initial position was slightly off origin as shown, and the initial velocity was zero since it started at rest. Before I could move forward to GlowScript, K needed to be calculated using the period of oscillation, which was found by using the times of two full oscillations and dividing that number by 2. Only the y components of the times were used for the period oscillation because the y-axis is the same axes the spring is on. I used the equations on the right to solve for K so that L0 could be found. In GlowScript, I changed the mass to be 0.402 kilograms and changed the initial position to be slightly off origin to match Tracker. I used the K and L naught that I calculated in the previous slide and inputted them into GlowScript as seen below. Once I had done this, I then changed L, L hat, and S so that they could match Hooke's law. The energy equations were also edited to match their definitions. On the right, I changed my while loop to include the entire time loop in Tracker. I also changed the force of gravity, the force of the spring, and F net to the appropriate expressions. I inputted Newton's second law for velocity and used the position update formula so that the change in energy could be calculated below by calculating S, L, and L hat again. The code outputted the following graphs. The change in energy graph shows a delta E of 0, while delta U spring and delta U grav oscillate opposite to each other. The X and Y positions were compared to the data measured in Tracker. However, the graphs do not appear to line up exactly. The computer model instead ends up being a poor reflection of the observed motion. This is most likely due to the lack of drag in the computer model, which would affect FNet and throw the motion data off. This can be seen in the graphs as the expected motion is slightly more than the experimental data since it does not account for the drag. It could also be due to a faulty mass tracking in Tracker since it was done manually. Now onto the lab questions. Is the energy principle satisfied? Yes. The change in energy is illustrated in the graph by the orange line at y equals 0. The energy principle is satisfied because delta E is constantly 0, meaning that there is no work done on the system by the surroundings, nor has energy been lost to the surroundings. No energy has been lost and none has been added, satisfying the energy principle, as seen with the orange line. Separate oscillation periods. To compute the separate oscillations, I used the same method as I did to calculate K as seen on the right. The Y component was used above, so only the X component needed to be calculated anew. The two components had a significant difference between them, which would have thrown off the K values and spring force as a result. Y was again used since it was the same axis as the spring, but had we used X, the results would have been as follows. X was larger than Y in this case because the spring moved more quickly up and down than it did from side to side, meaning that the spring bobbed up and down more times than it went from side to side. Thank you for listening.